For years, it seemed like the sun was setting on traditional solar cell technology. Plagued with issues that never seemed to end in years of stagnation, a groundbreaking revelation is about to dawn. The secret? A stellar 2D synthesis breakthrough that promises to transform the very foundation of solar cells. But here lies the million-dollar question. Could this method be yet another false hero? Let's find out together in today's video. But before we dive into what's causing all the buzz in the field of harnessing solar energy, let's spare a minute to talk about the concept of solar cells and some of the issues humanity has been plagued with in its quest to make the sun work for them. For the uninitiated, solar cells are tiny, square-shaped semiconductors that are made from silicon and other conductive materials that undergo manufacturing processes involving thin film layers. When sunlight interacts with a solar cell, it triggers chemical reactions that release electrons, leading to the generation of electric current. Basically, it is an electronic device that converts light energy into electricity. Beyond all doubt, solar energy is an incredible energy alternative. We can use it to replace fossil fuels like coal and gas, which produce air, land, and water pollution that is harmful to our environment and planet. However, despite the significant increase in solar cell efficiency over the years, mankind has had to face persisting challenges in the form of producing light harvesting materials like halide perovskites reliably at a large scale. Most commercial solar cells utilize crystalline silicon as the absorber layer due to its long-term stability, abundance, relatively low manufacturing costs, capability for doping with other elements, and the presence of a native oxide passivation layer. But here's where things get really interesting. The indirect band gap nature of crystalline silicon, while providing stability and other advantages, hinders its efficiency as a light emitter, restricting its solar conversion capabilities. In comparison to materials like perovskites with an exceptionally high light absorption coefficient, silicon requires 1,000 times more material to absorb an equivalent amount of sunlight. Jin Ho, a Rice University graduate student and lead author on a study about the process published in Nature Synthesis, producing 2D perovskite crystals with layer thicknesses or quantum well thickness, also known as n-value greater than 2 is a major bottleneck. An n-value higher than 4 means materials have a narrower band gap and higher electrical conductivity, a crucial factor for application in electronic devices. During the process of crystallization, atoms or molecules organize themselves into well-structured and orderly lattices as they form crystals. A good example of this can be seen in ice, which can even exhibit 18 different atomic phases or arrangements. Similar to oxygen and hydrogen atoms in ice, the constituents of halide perovskites can assume various lattice arrangements. For a while, scientists have been seeking means to produce 2D halide perovskite layers with a consistent single phase, as material properties depend on the phase. But there is one issue. Traditional synthesis methods for higher n-value 2D perovskites generate uneven crystal growth, which impacts the material's performance reliability. As explained by Ho, in traditional methods of 2D perovskite synthesis, you get crystals with mixed phases due to the lack of control over crystallization kinetics, which is basically the dynamic interplay between temperature and time. We designed a way to slow down the crystallization and tune each kinetics parameter gradually to hit the sweet spot for phase-pure synthesis. What we find to be truly amazing is the fact that the researchers not only developed a synthesis method capable of achieving a controlled increase in the n-value of 2D halide perovskites but also developed a phase diagram of the process using characterization, optical spectroscopy, and machine learning. Additionally, they developed a new method to improve crystal purity, resolving a long-standing question in the field on how to approach a high n-value in phase-pure crystal synthesis. Not only will these amazing research and groundbreaking developments expand the possibilities of synthesizing higher quantum well 2D perovskites, rendering them a feasible and stable choice for diverse applications, but they could also achieve commercially relevant stability for solar cells and many other optoelectronic device applications and light matter interactions. With everything that has been said and done, you're probably wondering why these solar cells are important to our everyday lives, right? Well, we're all seeing the concerning impacts of greenhouse gas emissions, aren't we? Right now, the transition to solar energy is not a choice but a vital necessity. Solar cells offer us a crucial avenue to substantially diminish our carbon footprint and reduce the possibility of climate change. However, apart from the obvious reason of being a cleaner energy source in comparison to fossil fuels, one of the most compelling reasons why we need to embrace solar cells is the fact that, unlike fossil fuels that can be exhausted, solar energy stands out as a sustainable resource that won't run dry. Like clockwork, the sun will rise and set every day. When solar cells capture sunlight and convert it into electricity, they do it without depleting our precious natural resources. This not only ensures a reliable and consistent energy source but also marks a crucial step towards breaking free from the shackles of finite energy supplies. Also, solar energy isn't just about being environmentally conscious, it's also a catalyst for economic growth. The solar industry has become a force to be reckoned with by creating jobs, fostering innovation, and attracting investments. Embracing the juicy prospects of solar technology wouldn't only lead to a healthier, greener world and serve as an investment in a fast-growing tech sector that could promote economic development. And to make things even better, these solar cells won't be restricted to areas that can afford to have electricity. The sun touches every corner of the earth, and these solar cells will work in remote and off-grid areas. Guys, in these regions, where traditional power infrastructure is impractical, solar cells can act as a lifeline, bringing much-needed electricity, empowering communities, and fostering development. Plus, when natural disasters happen or wars happen, no nation will be worried about power grids being shut down for a while. It's completely decentralized, breaking down the issues that come from monopolies. What could possibly go wrong? When you think about all of these, it's easy to see why solar energy is the future. The only reason why it is yet to be mainstream, or at least the primary source of energy for most homes, is the fact that they have been a bit unstable, and it's also been particularly difficult to produce light harvesting materials like halide perovskites reliably at a large scale. But, thanks to amazing engineers and scientists like those we talked about today, the ongoing technological advancements in solar cell technology will further increase its appeal and probably change the status quo way sooner than you think. We can't wait to see how they roll out. That said, we admit that science can be subjective. What's groundbreaking and exciting for some might just be an unnecessary advancement for others. Why don't you hop into the conversation by letting us know your thoughts on the recent developments regarding solar cell technology? Do you feel excited about it, or do you think there's still a lot of ground left to be covered?